It's fairly common these days. Anybody that needs the negative frequency this time of day. Whole box.
Testing 1, 2, 3.
Before we start, I wanted to mention that this is the last time the shirts will be here at the meeting. Henceforth, if you want a shirt, you're going to have to ask Andreas to bring you one a month later. So I know how impatient you all are. And so, you know, if you want one, now's a good time to just at the break, maybe ask Andreas if he's got your size. So it's a transition. And furthermore, if you're a creative guy and you can think about something exciting to do with t-shirts, perhaps for the next 4th day, now's a good time to start thinking about it. We have t-shirts. Yeah, a few left. But you're saying Brett doesn't want to bring the meeting in with t-shirts as Andreas. So Andreas is going to take orders and bring them the next month. which probably won't happen, but, you know, you should order, if you order my mail, email the money, goes mail to you.
It's time. Are your mic'd up, switched on, ready to go?
And I just got it. Well, yours, introduce yourself.
What?
Don Golding here. Don Golding here, and I'm going to be talking about the AIR project, the AI and Robotics project. But first, I have kind of a really important announcement. I want you to check out a really cool company. Oh, let's see. You don't have HDMI audio? This one here?
Yeah.
Yep.
Architecture and customer. Space is so cold.
Is it called madeinspace.com?
Yes.
Because everything was made in space. Pops and change the body.
Nothing, huh?
In the near term, Argonaut will make pieces like trusses or reflectors for satellites. But ultimately, the goal is to build spacecraft and
Start it over.
space stations.
That's the reason that we believe in, that the way we'll get to Mars and the asteroids and beyond is larger.
Where's the thing on the bottom?
Should be down there, further down.
Take for humans to colonize space, the team at Maiden Space thinks 3D printing is going to be key. That's why they're developing Argonaut, a floating robotic factory for 3D print and assemble large structures in space.
I think Argonaut is really key to enabling advancement of civilization in space. It's really key to getting us to Mars and beyond.
It's an absolutely essential step in the future history of our species to move off this planet and to inhabit every environment in the solar system that we can. It's not going to be done by importing everything you need from where you came from. It's going to be done by manufacturing what you need, where you need it.
Right now, it's expensive and challenging to get things into space. Every object must be small enough to fit inside a launch vehicle, and also strong enough to survive the rigorous environment. The International Space Station, for example, required individually launching more than 100 components into orbit.
So if we could build spacecraft in space, we could make them 10 times lighter and 10 times cheaper, because we never need to design them to survive the shake, rattle, and roll of launch.
In the near term, Argonaut will make pieces like trusses or reflectors for satellites, but ultimately the goal is to build spacecraft and space stations.
That's the reason that we believe in, that the way we'll get to Mars and the asteroids and beyond is larger scale spacecraft that you build on.
Maiden Space already has a 3D printer building parts within the pressurized environment of the International Space Station. And last year, it successfully 3D printed an item in a zero-gravity simulation chamber. Within 4 or 5 years, the company says Argonaut will be making large structures in orbit without any human supervision.
Where's humanity going to be in 100 years, 200 years, 300 years? So we can stuff here all of our existence, all animals have. I thought it would be so transformative to be a part of people leading off planet Earth. I really want to help make that happen.
So I started there. What? So I started there last week as a senior electrical engineer. So I am so happy. This is a group of brilliant guys, and they're all and it's an amazing place. It's at Moffett Field, Ames Research Center. So in fact, they're going to be looking for more engineers. So if anyone's interested, let me know. I just wanted to bring that up. So I'm so excited about that. Archinaut is going to be for building things in space. So that's one of the robots I'll be building, designing, you know, with the whole group. So I'll be doing kind of the embedded system stuff. Well, it's like any 3D printer. I can't remember the name of it, but there's a special filament that they use in space. But they're also looking at using some local materials for like filler for the filament. And they have like 20 research projects. They're heavily funded by NASA. Yeah.
I'm thinking going after asteroids, because you know there are 3 kinds.
Yeah.
You have the stony, which are basically silicon oxide.
Mm-hmm.
And you have the metal, which basically are iron nickel. Then they have the carbonaceous contrast.
Right.
Which is basically protects carbon. So I mean, right there, you could have carbon filament. They do that. One problem is we have to do a survey of our solar system to find out where all these nice little things are.
Yeah, there's research going on in that area. They're doing some materials research as well. They have a you know, PhD guy who's working on that. He just got a new he got phase 2 funded on his research. So it's really exciting. Right. Yeah, but you know, the filament's pretty lightweight, so you can haul up a lot of filament. Yeah, in the beginning. In the beginning, yeah. Yeah, so one of the things that's interesting about what they're doing is they're making 3D printer that's basically it prints beams, and it's basically to infinity. So they have a beam that's hanging from the ceiling down the hallway from one side of the building to the other, and they got a Guinness Book of World Record for the longest additive manufacturing, you know, piece. And they just had one of their machines just kept going, and I didn't say, yeah, I heard it at a meeting last week. I don't remember exactly what it was, but it's a polymer based material, as I recall, but it's you know, works in space.
Space is rather harsh.
Yeah.
You know, the oxygen that you and I have get up in space, and it becomes
Right. Yeah, and you know, if you think about I had 5 interviews to get into that company. It was pretty amazing. So I had a phone interview with the CFO. Actually, she was kind of the human relations, and then I had the president, and then 3 engineers. We did a phone con, and then I talked to Mike Snyder, who's their senior engineer, and he's in some of these videos. And then I had a face-to-face. I had 5 interviews. A quarter of the company interviewed me, basically. It was pretty amazing. But one of the questions that I was asked, because you know, there's my last meeting, there's 2 MEs in the room, and they said, "What do you think? You know, one of the hardest things in space is?" And the questions the interviews were actually very interesting, because the questions they would ask were fascinating topics just to, you know, talk about. But, you know, I said, well, if you got a robot and it goes to grabs onto something, and if it misses, that something's going to be going that way, and the robot's going to be going that way, you know. But I'm sure everyone will answer that a little differently, but that's how I answered that one. So there's a lot of, lot of issues. We have, we're going to have to be doing navigation and stuff, out there, and we can use GPS, but, we were talking about that too, and they go, well, what another question they ask, I shouldn't tell you guys, it might go get interviewed sometime. Another one they asked is, besides GPS, what else do you think we could use? And I said, well, I could use a star tracker, like point the video up. And then I was thinking, well, you could even point it down at the Earth.
Yeah, they have Earth sensors.
Well, no, I'm just saying that, the image of the Earth, your position, right? Because they're very unique features. So it's
Broadcasting, going right by you. Look at them.
Oh, that's a good idea.
They do have Star Tracker and Earth sensors, but my previous job that I worked on, I remember seeing that stuff. Well, also you want to make sure that your orbital elements don't change.
Let's move on to the robot.
Okay, so on to the robot. Let's see. Come on. All right, so let's see. Okay, one thing I want to show. So we're using the ESP32 processor, which is, this might not be the exact one, but this is one of them. And, they're like $4, $3 to $4. And like Dr. Ting was saying, it's a module. This isn't the pinned one. This is the module from the factory. So that's what we're using is this one. And, it is an amazing processor, with Wi-Fi and Bluetooth on it, 32-bit. And we're going to have Dr. Ting's 32-bit fourth to be, working with. And he's porting the language over, my language from Whiskers over to it. So at the Maker Faire, we should have working robots. That's what I expect. No, this is, yeah, so what I wanted to do is make it open source, open hardware, and get it out there and get people using it. It'll help. One of the problems I had when I developed this language and everything is, I had a family. I was trying to support them. I mean, I did support them, but I had to make money. So I developed the language and everything, and then I focused on selling robots, which I sold over 2,000 of them. But I didn't really spend a lot of time on developing the application level software in the language, and no one really picked up the ball. So my robot was 25 years old, through whole parts. I didn't bring it. Well, it's in my truck, which is being repaired. But anyway, so this project is going to be open hardware, open source. Right now, anyone that sends me an email, I'll give you the schematics. I want you to go ahead and review it. It's not open source, open hardware today. let's get it working first, and then we'll do that, because I don't want a bunch of stuff that doesn't work out there. You know, so let's get it working first. So we'll introduce it at the Maker Fair as open hardware, open source. Up until then, glad to share things with everyone in the group, and like to have your inputs as we develop this. So I'm working on the hardware. Dr. Ting's working on the software. So this is the processor, and I did put an SD card on it. This is the JTAG right there, and then there's a boot option that's required for that. Let's see. I'm open to input. I haven't really played around with the SD stuff that much, so by all means, you know, steer me. Yeah, I want to make it simple and easy. We don't have to be state-of-the-art SD cards. You know, let's. Uh-huh. Okay, send me an email and, you know, give me some support on that. Or anyone else that, yeah. Mm-hmm. Mm-hmm. Okay. Okay. All right.
One thing you could do if getting SD cards working with that gun is more difficult than I thought it would be when I started to work on an SD card driver is to use a SD card sniffer, which is two steps. It breaks out the pins in between the SD card and your computer. Use that to record whatever it's doing when you like read or write or visualize the SD card from Linux, and then just capture that and replay it.
Oh, okay.
Every SD card is a little bit, all these different brands work a little bit different, and they're not.
Great.
There are three different basic ways to visualize it. It depends on what level they are. But they are documented. There's a web page that tells you get down to this point, it doesn't come back with any dollars, and then you do this or that, this or that.
All right.
It's more complex. For me, I get one piece of hardware, I put it in there, and I was.
Does the regulator have to be programmable?
Yeah.
Oh. Okay. I so much like KISS. Okay, well, we might want to pick a line of SD cards and just support that line and have a single. I don't mind putting a regulator on there, but I don't want. Okay. All right. So this is the switcher. So you got the 12 volts coming in, and just a basic switching regulator creates the 3.3 volts. I do need 10 volts for the sonar. So this is, I just use a passive because the sonar doesn't take any sort of current whatsoever. So that generates 10 volts from the 12 volts. And Let's see, and then that's just, oh, that's just a connector. I have a Holy Point ground. So, you know, we have analog, it's a mixed signal design. So we keep the ground plane or the ground flood area for the analog separate from the digital. So this is not my normal way I do H bridges. Normally what I do is I have complementary P channel and N channel, and then another signal FET to bring the voltage up to 12 volts. But I'm trying to simplify this, make it cheap as possible. So I'm using the open collector inverter here. And and I wanted to get it down. We have limited pins on the chip. 28 sounds like a lot, but when you're throwing lots of sensors and I/O on it, you use them up pretty quick, and I've used them all. So by using this logic, I've cut it down to direction and enable signals. And then you just pulse width modulate it. So there's a current sense resistor here, and that signal goes down to some 358 op amps. So that, you know, amplifies the voltage by 10 or 20, I forget what it is, depending on these two resistors here. So that goes into two ADC channels. And if you remember, when I had Whiskers running around, you could grab his wheel and he would sense it. So that's how you sense. His whole body becomes a sensor, and it's the left and the right, right? Because one's driving the left wheel, one's driving the right wheel. So you can detect and you can react to motor stalls. In fact, it's sensitive enough on Whiskers, I could actually see a difference between a hard floor and carpeting. So the robot would actually know if he's on carpeting or a hard floor. And you could create some sort of behavior, you know, if you want. Let's see. So just like my first Whiskers, I wanted Whiskers to have as many sensors, you know, like my analogy is like a cat, right? So so we have two-stage amplifiers. So one of them is for a microphone, and the other one is for sonar. I decided to put sonar on the base platform PC board, just in case people didn't want to go put the head on it. But there's going to be another PC board that plugs in and be networked, maybe over I2C. And then we can have another microprocessor that's doing some long range, like scanning for the door and that sort of, and maybe put a laser on it. But this way, with a basic board, you can see out 20 feet. And I'm using the piezoelectric sonars. And last time I gave a talk, I talked about the algorithm that I used to develop the sonar, and maybe I'll say it again because maybe some new people here. So what I do is I chirp the transmitter one time, and then I digitize that. I chirp it 2 times, I digitize that. I put it in a 2K RAM buffer, 8-bit, and then you can see it come down, and then if it sees something, there's a jump. So basically you're looking for, it's a peak detector kind of algorithm, right? And you have some sort of threshold that if the peak is greater than 5, then it's a hit. So what's really nice about that is the robot can see right up to its face all the way out to 20 feet. So you go 1 ping, 2 pings, 4 pings, 8 pings. And through experimentation, I found 20 pings at 40 kilohertz, so it's pretty fast. 40 pings is where the transducer gets in maximum acoustic oscillation. And so I stop at 20 pings. So you have both You have both ultrasound and a microphone. We also have a speaker, so you can have him play orchestra. I only have a single speaker. I don't know, you had stereo in your demo, but maybe you can get one speaker's fine. Okay. Yeah, I was very impressed. I mean, and the speaker on Whiskers was really a pretty terrible speaker. Actually, if you put a regular speaker on Whiskers, it sounds a lot better. So we'll have a good speaker on it. Well, you know, I'm talking about a 2-inch. You know, they're 25 cents out of China. So, so this is the you remember the LED, the 4 LED. It's a LED and photo Darlington pairs on Whiskers. So you had 2 side ones and 2 forward-looking ones. That's this right here. What I had some extra I/O left, so what I did was I added some half bridges. Now, what's interesting about this is you can take the airplane servos with one single half bridge. You can drive an airplane servo. So you basically pulse width modulate it at the correct frequency. It's like a kilohertz or something. I forget the exact frequency. And then you just change the pulse width, and then the servo motor will position to whatever the pulse width is. So you could put ears on the thing and have it flapping, or do facial gestures or something like that. You have 4 channels for that. So yeah, that's basically the design at the moment. I have to add one more circuit. I talked about how important a compass is. After I designed Whiskers the first time and I was playing around with navigation and stuff, I found I really needed to have a compass. It's great to have the goal level saying, hold this compass heading, then the instincts and behaviors when it sees something will deal with that and go around, and then it goes back to the same compass heading. It made navigation across the room really easy. So I'm going to add an electronic compass to it. That's what I'm going to do in the next week or so. A what? Hall effect?
So it can sense the magnetic. And I don't know how good it is, but I was testing the ADC. I got that magnet over it, and then got different signals. So if it has an integrated Hall effect sensor in it.
Oh, that would be interesting. I'm going to put a.
I don't know how good it is.
Yeah, I'm going to put a compass on it. They're cheap. What?
Hall effects are just, they're right at the edge of earth detection. In other words, you can see it, but it's not real strong. Whereas with the fluxgate, you can clearly see first magnetic field. And it's a different way of doing it. It has to do with saturating the pores and using the Earth's magnetic field to bias the core. So you look for that saturation. They're fairly simple, but they do take a power, or not a power, but you don't have to, if all you're doing is just giving an instantaneous coordinate, you do that very so really first, like the chirp of your sonar.
Yeah, I'm putting a 3D sensor on it. So yeah, you're going to have an accelerometer, a magnetometer, and what's the other one? Anyway, you're getting all 3. I have a really great algorithm in C, which I'll give to you, and you can make it in 4th, or you can compile it and make it a 4th word. And what it does is it takes there's 4 outputs to the magnetometer, and the robot spins in place, like does a 360 degree. It finds the min and the max magnetic field, and then it knows magnetic north. And so it calibrates itself. If you look at some of the stuff on ADR Fruit and some of these other places, you have to give it what do they call it, delinearization, or in other words, you have to give it a parameter of where you're at on the planet, because the magnetic fields aren't the same, don't go the same way, and you have to give it that parameter. But with this algorithm, my friend Dr. Tom Waite actually developed it for me. He's fantastic. He's on our team too. he was he's a PhD electrical engineer, and he came from Northrop. He was a senior engineer over there, heavy mathematics. So anyway, I gave him some raw data. I gave him like several pages of raw data I got from the accelerometer. And I gave him an app note from Honeywell, and I shot it up to him. And 3 days later, he gives me this algorithm, you know, which is a little different than what you get off the web. And it works so sweet. I went to a sporting goods store. I was looking for a compass, you know, just a regular old compass, you know, with a liquid filled. And they're going, what is that? and they're looking all over the store, and they got all these electronic compasses and stuff. And there was like some bubble packs hanging on the corner, and we're looking in there, and there it was. And so I got it, and I used that to check it, and it was amazing how well it worked. So it's going to have a really good compass on it. So this robot is going to really have a lot of senses. So we can do a lot of work in AI, and it's going to be very low cost.
You know what variation and deviation is?
Yeah.
Oh, so he's already taken care of that thing?
So, well, when you spin in place, it gets the min and the max of both of the magnetic fields,
Right.
and it calibrates to that location.
Okay, so that's your variation. Right now, that's your deviation. Yes. Then you have how the external magnetic field is.
We're using it like in, you know, in a small area.
Oh, small area.
Yeah, it's not going across country.
No, then all you have to do is just variation in that area. So just
No, you don't have. I'm saying you don't have to do it.
You're gonna stay magnetic.
We're staying. Yeah, we don't need to know true north. It's a relative sensor. Yeah. Right. Yeah. We just need to know, you know, we need a sensor that gives us position, you know, angle on Earth, where we're at. We don't need to know that it's actually 0 degrees or 10 degrees on a compass.
That's like with the way they number runways.
Yeah.
That's magnetic, not true.
Right. Yeah, we're not calculating true. We're just using magnetic. But when the robot spins, it's calibrated to the magnetic field lines of the location it's in, and you could probably go, you know, 100 miles plus or minus, and it would still be fine. Huh?
It's a very smart Roomba.
Don't get me started on Roomba. I know Helen Granier personally. Yeah, the important thing about navigation is I found that the compass was really critical because, you know, it's not going to have, the only long range sensor it's going to have is the sonar. And so with the sonar, it could find a door 20 feet away by rocking back and forth, right? And say, oh, there's the door. Well, as soon as you stop and rock back and forth, you know the door is at 346 degrees. And so then you would go there, and you could, because you can read the compass as you're moving, you could actually calculate how far off you are, but you can stop and recalibrate at any time. So you can imagine this robot, you tell it to go find the door, and it will find the door autonomously. How many robots can do that today? And it's not that I was doing this 25 years ago. I don't understand why robots aren't smarter, but anyway.
The robots can find the plug, the electricity on that. So you can go when the battery is low, you'll go
Yeah, you could do that with this robot. See, remember, it's got 4 optical, optical Darlingtons on it. So that are sensitive to IR. So you could either, well, I like using visible light for 2 reasons. I did some testing with visible light and IR. Like I took a piece of black velvet, and I wanted to see which one could see the velvet. The IR was totally absorbed by the black, but the optical, although it attenuated it, I could still see it. Maybe I could see or something reflective 12 inches away, but I could still see the black velvet maybe 2 inches away. So the optical is more fun because you see some lights flashing and they're actually doing something. They're not just flashing. But these sensors do detect IR. So if you wanted to make IR beacons, like put the charging station somewhere, we're going to have a secondary board for the head. I showed the advanced whiskers during my last talk, where we had 2 microprocessors, one that had a head that could move around and look, and we'll be able to do that with this unit too. We could put GPS on the board, and put a second sonar and maybe a laser, and then we can do some navigation kind of stuff. That would be a super intelligent robot. But a funny Roomba story. So this is back about 1993, and I designed my whiskers robot. And I designed it for not to solve or not to do something. It was to show off my my 3-level software architecture for people to experiment with. So it's really a platform to experiment with my software. But I'm looking at the thing one day, I'm going, can I make this thing actually do something productive? And I was thinking about that, and I went into an AutoZone store, and I saw this little 12-volt vacuum that you plug into a cigarette lighter for your car. I could power that. So I grabbed the vacuum and I go back and I mounted it on the tail of Whiskers, and I plugged it in because Whiskers is 12 volts too, so it was no brainer. But Whiskers could only randomly run around. I said, nobody would want that. It wouldn't do a good job of, I'm thinking like an engineer. Well, the people love Roomba not for it being able to vacuum. It's because like a pet. If you think about it, Roombas don't do that great a job because how can you do a good job when it's random? So, with the compass, a compass and Whiskers, you could build a super smart Roomba because you can now do, like sowing a field, right? And then the instincts and behaviors will get around the dinette set, and then you could go back, on course again. So, you can make, I think they just came out with a Roomba that can do that this year, right? Yeah. They've sold $1 billion of those things.
Why aren't you rich?
That's what I keep asking.
With your robot, what is the biggest, are you actually essentially having the robot build a model of the space it's in? What's the biggest, the most complex space you've ever had your robot remember?
Okay, that's a really good question because you're thinking like Marvin Minsky and Hans Moravec. So I got back in robotics, which was about 1989. I heard that there's a robotics group that was meeting at this college, and they were restarting the Robotics Society of Southern California, and the internet wasn't available back then. So I had a phone modem, and I used to dial into a VBS called Interocitor in Texas at 1200 baud, but they were mirroring DARPANET. So I was reading comp.robotics, and I was reading about how Hans Moravec and Marvin Minsky, Moravec from Carnegie Mellon and Minsky from MIT, they had this robot, I think they called it Shaky, and they were doing exactly what you were talking about. They're doing navigation in a room, and they had the most powerful processor they could get, and the thing would go 1 foot, look around the room, update its maps and its world model and everything else, and then it would go another foot. Well, when they were doing that research, a fellow named Rodney Brooks was a graduate student, and at MIT, and he was sitting in his office and he's watching a fly, and and he swats the fly, and the collision avoidance with a fly is amazing, right? 1,500 neurons in a fly. So he came up with the idea of subsumption architecture. So basically you have layers of functions, like so the bottom function is going forward, and then a sensor, the sensor in the front sees something, it triggers the next one up, which is turn left or right to do collision avoidance. And so you stack all these things up. The problem with Rodney Brooks's subsumption architecture is you couldn't really give it a goal. It'd be great for it did really good at collision avoidance, but you couldn't give it a goal. And that's where I came up with my idea, is I said, these two ideas should be merged, ideally. So then I created the instinct level, which is like is a motor sensor fusion at that level, and that's a background task. So that happens automatically in the background. So if a whisker sees something, it's going to rotate, no matter what the goal level or the behavior level is trying to do as far as giving it a motor command. The instinct level has top priority. But it's the lowest intelligence. Anyone not hear my talk on that?
New Yorker covered this about months ago, about this whole problem of what is intelligence. It's not logic, it's reaction to circumstances to a large extent.
Absolutely. That's a great way to put it. That's a perfect way to put it. Yeah. So I call it servoing on the environment. Instead of servoing on a sensor, you servo on the environment. Bigger loop. Servo on that door, right? Don't servo on a sensor. So anyway, so I created a 2-level. So I had a goal level, and it was trying to go, its idea was to go forward, and then the instinct level was collision avoidance. Well, what happens when the robot, the left whisker sees this one, the instinct level pulls it back, and then it goes forward as soon as it doesn't see it, right? Because it's instantaneous. And then the right whisker hits that one, so it oscillates. Well, it needs to make a decision. Now, if you want the goal level to have this humongous case statement, that kind of defeats the purpose. So I said, okay, I need this middle level, which is, I call it the behavior level, and it's my set of behaviors. So if I get both a left and a right whisker hit, I'm going to the behavior is back up, turn, then the behavior terminates. That's it. What?
It knows whether it can go through the models.
What?
It has to know its own width, its own size.
No, it doesn't have to know that at all.
That's what he's trying to avoid, trying to make.
Yeah, see, that's exactly the thinking that Marvin Minsky, you had to model the world. You don't have to model the world, to get around, to navigate.
You have to have a way to make a choice.
Yes. So, and because I'm a fourth programmer, it's bottom up. It's obvious to me. It may be not obvious to,
Code bottom up, design top down.
Yeah.
Well, but the organism is designed.
So what you wind up doing is you think of all the situations the robot gets into, and you create a behavior for the situation, and then you put them on the task list in a prioritized fashion, and then the behavior will emerge and take care of it as soon as it gets in that situation. Now your goal level, see, you don't have to have this big case statement in your goal level. You know, if I'm in this situation, do this stuff. The goal level could just say, hey, I'm looking for that door. And then the instincts and behaviors do collision avoidance as it goes over there. So it just breaks up the problem into a really nice conceptual, you know, hierarchy.
What does the intelligent organism doesn't try to go narrow aperture, might be caught, it tries to find a way around.
Right, yeah, I mean, you know, you have bugs that do that, you know. So they're not figuring out the model of the environment. So anyway, I call it the Triune OS, and I was at a trade show and I was talking about my robots to a lady, and she was heavily a biology type person, and I'm describing the functionality of my 3 levels. She says, "Oh, that's the triune brain," and I go, "What's that?" And I looked it up. You look it up. Look up the triune brain on the internet, and the functionality is the same. So you have your reactive, you know, your nervous system and brain stem. You know, you touch something hot, your nervous system pulls it back before you even have time to think about it, right? I mean, as soon as you touch something hot, then you start thinking about it. So that's the way the instinct level works. And then the limbic system is like, you know, my breathing is automatic, but I can override it too, right? I can hold my breath, but it's automatic. So I don't think about breathing. So there's, so the limbic system, if you read about how it functions, it maps very closely to my behavior level. And then the goal level becomes really simple. So you can, you know, the goal level is just, you know, I want to go out the door. You know, so I'm looking at the sonar, go that way, you know, behaviors. So I have, in the behavior level, I have a compass behavior. So it automatically, the goal level tells the compass behavior, I want to hold this course. And it's trying to hold the course, and of course, if it sees something, the instinct level has priority. It avoids it avoids it. And then the behaviors also can interrupt the compass. So the compass heading is really a task. So you can have tasks and behaviors. So the front part of the list are tasks, something you want to run all the time in the background. So like if you're trying to hold the compass setting, it'll say, okay, I'm off by 3 degrees, so I'm going to adjust my motor speeds. And then when it continues down the task list and it actually sees something in front, that behavior will trigger and go around it. And then the next time the task list gets fired, which is 100 times a second, it'll go, oh, now I'm off by this much. Well, adjust your motor speeds this way. So the interaction of all these behaviors makes for a very intelligent machine. And simple, it's simple to program. It's like teaching a child. You're in this situation, do this thing. So one of the things, when I started coming to the 4th group in September, Dr. Ting was talking about his searching algorithms, and I was really excited about that on the genome searching algorithms. And I said, that's what we need for a robot. We need a robot to build a database of sensory patterns that we can do a fuzzy search on, and then a solution. So, you know, a database of, you know, the patterns, and it needs to be a fuzzy search because it's not going to be exact. And then, you know, what worked last time. So with this robot, you can please do. I'm looking for people to do that kind of work because, you know, I'm too busy to do everything. That's the whole point of all this. Yeah, thankfully. I hate that when it happens. So the learning, so with the learning algorithm, what you're going to do is that's going to be your goal level. You're going to spend a lot of time on that, but you may find that you want to have some, maybe 100 times a second as part of your learning algorithm. Okay, so let's say we build a neural network at the goal level, and we want to update the neural network. Well, you can create a task in the task list that is updates all your neurons, right? So the whole system is there for you to develop, you know, even memory. Triune, triune brain. Yes, exactly. Fuzzy logic. Yeah, remember there's a prologue fourth book, prologue in fourth. There's a lot of people did AI stuff in fourth, and I'd love, you know, for us to revisit those things and apply them to the robot. We had one guy talk about Lisp. He did Lisp in fourth, and you know, the beautiful thing about fourth is you can build anything. If you see a cool language and you like certain things, create does, right? Yeah, we should be getting back into that stuff and seeing what kind of stuff we can apply, because we got a 32-bit processor. I mean, this thing is going to be smoking, and you know, you're going to be able to you know, have an I2C interface, for example, and you could plug in as much power as you want, you know, if you're doing some sort of research. And oh yeah, that brings up another cool thing. So I was curious one time. I was playing around, you know, searching, and I did a search on Deep Blue. And do you know IBM lets you use Deep Blue for free? Yeah, so they have an API. So our little robot could go talk to Deep Blue over the Wi-Fi. How cool is that? You couldn't do that in 1990. You could do anything you imagine, and please do, and share it. You know, that when we get this platform running, and you know, people get it in their hands, you know, it's going to generate a lot of talks on AI and robotics. So I want to. Yep, I'm doing that. Okay, so there's my email address. So please write it down and send me an email if you're a hardware guy and you want to review the schematics. Just keep it, you know, let's keep it in the family right now. I don't want it out on the internet. We'll make it open source when we have it all working. I don't want a bunch of stuff that doesn't work out on the internet. That would be bad. So, so send me an email. If you're a software guy, and most everyone has Dr. Ting's email address. He's in charge of the software, or you can send it to me, and then I'll forward it to him. He's porting my whole Triune OS language /language over to it, and it only is 32K of compiled code for the whole thing. So it'll reside in Flash, and then the RAM in in the processor, you know, is where you can develop all your fourth code. We're going to be able to save stuff to Flash. Don't know yet. Yeah. So on my Whiskers robot, it always had a battery, and so I had battery backed up SRAM. And you typed in a word called remember. You turn the robot off and on again, and it remembered all your code. So hopefully we can do something. You know, worst case scenario, we'll do it the same way. I'll just have a battery on the processor all the time. Okay, good. Well, maybe you. So help me with this problem. Right. Yeah, send me an email about the voltage issue.
I don't know that.
Okay, well, if it bites you.
I'm aware of it.
Okay.
I don't have any parts now that actually start, but I know what they are. And that article that, I don't remember the guy's name, somebody Chang or something like that. He has an article on the web about initializing SD cards. He describes that basic algorithm you want to go through depending on what type of SD card you have in there. And in it, he describes about reading the voltage, ID back from the SD card, the voltage reload you're on from the SD card. And I think with initialization, sure.
Let me just.
Let Jack plug in for the first few minutes.
Okay.
Version or side trip or whatever.
It's not complicated. It's just an additional piece of noise. You can be able to just make the SD card work. And then we need there are three fundamental inits that you need for SD card. I use
Okay. There we go. So did you want to go?
32 chips. Right? So because they don't understand it,
We got to go. So.
Just think it's doing something else, and causes it to lock up. So you have to know how to unlock it in order to get it to always work. And that's what I figured out was how to do that.
Well,
But I did that.
let's thank Don.
Yep, thank you, Don.
While we're at it,
Yes, and Ting. Right. And now we have to shut down the stream. We'll see you next month.